Hello, welcome again. In this session on the discussion of second law of thermodynamics, we'll work out some numerical examples. We calculate work and heat interactions of heat engines, calculate efficiency of heat engines, calculate COP of heat pump and refrigerator. Let us consider this example. Determine the heat to be supplied to a Carnot engine operating between 400 degrees Celsius and 15 degrees Celsius and producing 200 kilojoule of work. This is the heat engine. Source temperature is 400 degrees Celsius. By adding 273.16, you have to convert this into Kelvin. This is a sink temperature, 15 degrees Celsius at 273.16. Work produced by this heat engine is 200 kilojoules. We need to find out what is a Q1. So we know that Q1 by Q2 is equal to T1 by T2. We developed this relationship while discussing absolute thermodynamic temperature scale. Anyway, from first law, we know this W is equal to Q1 minus Q2. So T1 is 400 plus 273, we ignored 0.16, 673, and 273 plus 15 is 288, Q1 by Q2. W is already given, Q1 minus Q2, W is 200 kilojoules. And this relationship also we know. By solving these two equations, I'll be getting the value Q1 and Q2. So this is what exactly the amount of heat supplied from the source to the heat engine. This is the amount of heat rejected to the sink. So remember these two relationships and we can easily solve this example. A refrigerator operates on reversed Carnot engine. So it's a reversible engine. Determine the power required to drive the refrigerator between the temperatures of 42 degrees Celsius, 4 degrees Celsius. If heat at the rate of 2 kilojoule is extracted from the low temperature region. Sink temperature is 4 degrees Celsius. It is added to 273 to express in Kelvin. Source temperature 42, 273 plus 42. This is a reverse engine. Instead of producing work, it will absorb work. So work is supplied. So we need to find out what is the amount of work that is supplied. So now you know T1, you know T2, you know Q2 value also 2 kilojoule per second or 2 kilowatt. Again, you know this relationship. From here, you can find out Q1 value. So work is nothing but Q1 minus Q2. Q1 value substitute here, Q2 value substitute here, we'll get the power required. That is power required for driving this refrigerator is 0.274 kilowatt. A reversible heat engine operates between two reservoirs at 827 degrees Celsius and 27 degrees Celsius. Engine drives a Carnot refrigerator maintaining minus 13 degrees Celsius and rejecting heat to reservoir at 27 degrees Celsius. Heat input to the engine is 2000 kilojoule and the net work available is 300 kilojoule. How much heat is transferred to refrigerant and total heat rejected to reservoir at 27 degrees Celsius? While doing the calculation for heat engine, this becomes the source, this becomes the sink. While doing the calculation for refrigeration, this becomes the sink and this becomes the source. So let us find out the parameters required. You know very well Q1 by Q2 is equal to T1 by T2. So Q1 by Q2 I have substituted for heat engine T1 value and T2 value. Out of this Q1 is 2000 kilojoules. It's known to us, so that we get Q2 is equal to, from this equation, this value. And work produced by the engine is nothing but Q1 minus Q2. This value also we get. Now let us consider for refrigerator. Q3 by Q4 is equal to T3 by T4. Okay. So again substitute the values, you'll get. Again the work of the refrigerator is Q minus Q3. Correct. WE minus WR is given as 300. WE is known, then you can get WR. Right? So Q4 minus Q3 is nothing but this value. Work absorbed by the refrigerator. And you know Q3 Q4 relationship. From this you can get Q3, this you can get Q4. Total heat transfer to low temperature reservoir is Q2 from the engine and Q4 from the refrigerator. Add Q2 value as well as Q4 value and you will be getting this. So heat transfer to refrigerant is 7504.58 kilojoule and total heat transfer to low temperature reservoir is so much. So this is the one, this value and some of these. In the winter season, when outside temperature is minus 1 degree Celsius, the inside of house is to be maintained at 25 degrees Celsius. This clear case of heat pump. Estimate the minimum power required to run the heat pump, maintaining the temperature. Assume heating load as 125 megajoules per hour. So COP heat pump is given by Q1 by W. W is nothing but Q1 minus Q2, or you can write like this, 1 minus Q2 by Q1. You know the relationship Q1 by Q2. The temperature values are known. Okay, atmosphere is 25, 273 plus 25, and this one is 273.16 minus 1, or 273.15 is taken over here. So thus COP of this value substitute here, you will get the COP of heat pump. COP is also equal to Q1 by W. So now COP is known. Okay, Q1 is known. You can find out what is the W. So Q1 is 125 megajoules per hour. Correct. You can also express work in megajoules per hour, or you divide by 3600 and you will be getting kilowatt. Right? Fine. Minimum power required is 3.02 kilowatt. Again, take another example. A cold storage plant of 40 tons of refrigeration capacity runs with its performance just 1/4 of its Carnot COP. Inside temperature is minus 15 degrees Celsius and atmospheric temperature is 35 degrees Celsius. Determine the power required to run the plant. Refrigerate, power required to run the plant. This temperature is minus 15 degrees Celsius. This is 35 degrees Celsius. Q2 abstracted is this. We can find out Q1, then you can find W. Correct. Carnot COP of plant, that is you write Q1 divided by Q1 minus Q2, reorganize and find COP. Correct. Then a cold storage plant of 40 tons refrigeration capacity runs with its power. It's a real plant, one fourth of that. You will get the COP. Q2 is known. Bring W here, COP here, you will get the W value. So this is the power required to run this plant. What would be maximum efficiency of engine that can be had between the temperatures of 1150 degrees Celsius and 27 degrees Celsius? Carnot engine 1 minus QL by QH, or it is TL by TH, or you can say low temperature and high temperature. Substitute, you will get the efficiency of the reversible Carnot engine. A domestic refrigerator maintains temperature of minus 8 degrees Celsius when the atmospheric air temperature is 27 degrees Celsius. Assuming the leakage of 7.5 kilojoule per minute from outside to refrigerator, determine power required to run this refrigerator. Consider refrigerator as Carnot refrigerator or reversed engine. So you know the values of temperature 27 degrees Celsius and 8 degrees Celsius. So also you know COP is equal to, that is heat to be removed and the work supplied. From this equation you are going to get the work. So power required is 165 watt, sorry, 0.0165 kilowatt, 165.5 watt. Three reversible engines of Carnot type are operating in series as shown between the limiting temperatures of 1100 K, 300 K. Determine the intermediate temperature. The work output from the engines is in proportion to 3:2:1. First engine, second engine, third engine. First engine will give 3 times, second engine 2 times, and third engine will give 1 time. So efficiency of heat engine is W1 by Q1. It is nothing but 1 minus heat rejected by the first engine 1100. Okay, from here you can find out the Q1. W2 by Q2, it is 1 minus, again efficiency of the engine 2, T3 by T2, and efficiency of heat engine W3 Q3, 1 minus 300 by T3. Now we need to solve these equations to find out what is T2 and T3. So you know Q1 is equal to W1 plus Q2, or you can say Q2 is equal to Q1 minus W by subtracting this W1. So Q1 by, W1 by Q1, from that equation Q1 is equal to W1 T2 by 1100 minus T2. For engine 2, work output of that engine, the heat that is supplied, okay, that is equal to 1 minus T3 by T2. So W2 by W1 ratio, if I reorganize, I'll get this. It is 3 and this one is 2, the ratio. So 2 is to 3. So 2 by 3 equal to this equation I'll get. So cross multiplying, I'll be getting this equation. So I got one equation. I need to get one more equation to find out T2 and T3 values. So this is the figure, arranging all the three engines. Similarly, energy balance on engine 2 gives Q2 is equal to W2 and Q3 plus Q3. Okay. So this becomes the heat supply. The work output is of this engine is W2. This is nothing but efficiency. Again, in terms of temperature, I can write like this. So from this equation, I can find Q3 value. So I know what is the heat supply to this. Work output of that is W3 and heat supply to this I will write like this. And these are the temperatures T3 minus 300 by T3. Then I'll get the relationship between W3 by W2 in terms of this. W3 is nothing but 1, W2 is nothing but 2 because ratios are given. From that I'll get this equation. Now I got this equation. Earlier I got this equation. If I solve these two equations, I will be getting T2 and T3 values. A Carnot engine getting heat at 800 K is used to drive a Carnot refrigerator maintaining 280 K temperature. Both engine and refrigerator reject heat at some temperature T. When heat given to engine is equal to heat absorbed by refrigerator, determine the efficiency of engine and COP of refrigerator. Engine work output by heat supplied is also equal to T1 minus T2 by T1. So 800 K. So that is what I have written. T is the temperature at which it rejects. COP of a refrigerator, it is heat abstracted, that is Q3, and work supplied is W. So this I can write again T3 minus T by minus this temperature 280. So I'll get this. It is given that Q1 is equal to Q3 is equal to Q. So Q1 Q3 is equal to Q. So I'll get W by Q, this equation, and Q by W I'll get this equation. There are two unknowns, two equations are there. Solve this and I'll be getting the whole thing, right? So temperatures I'll be getting. So efficiency of what is the substitute back, I'll get the efficiency of the engine. Also, I'll get the COP of refrigerator. Point 0.5 kg of air executes a Carnot power cycle having a thermal efficiency 50%. Efficiency is 50%. Carnot efficiency 50%, mass is 0.5 kg. The heat transferred to the air during isothermal expansion during process 1 to 2, okay, is 40 kilojoule. This is TS diagram. If I draw PV diagram, this is 1 to 2. The heat transfer to the air during isothermal expansion is 40 kilojoules. This one is 40 kilojoules. It is nothing but Q1. At the beginning of isothermal expansion, the pressure is 7 bar and the volume is 0.12 meter cube. This is 7 bar, this is 0.12 meter cube. Determine the maximum and minimum temperature for the cycle in Kelvin. The volume at the end of the isothermal expansion in meter cube. You have to find out here. And the work and heat transfer for each of the four processes in kilojoule. For air Cp is given, Cv is given, right? So there is one more process like this, adiabatic, again compression, again adiabatic. This is what Carnot cycle is. So efficiency of the Carnot engine is 0.5, mass circulated is this thing. what he says, at the beginning of the isothermal expansion, the pressure is 7 bar. Okay. I think here the process written as 2 and 3, and I have written as 1 and 2. Okay. Let me say 2, 3, 4, and this I call it as 1. Okay. Right? 2 to 3. So now definitely this temperature is T1 and this temperature is T2. These two are adiabatic processes. Adiabatic expansion, adiabatic compression, isothermal expansion during which heat is supplied, isothermal compression during which heat is rejected. Okay, this pressure is given, pressure that is P2. Also the volume is also given. So efficiency of the Carnot engine is 1 minus T1 by T2. You know the efficiency value 0.5. So I get T1 by T2 is equal to 1 minus, if I subtract, I'll get 0.5. T2 is equal to 2T1 I'll get. Correct? From, you must have studied in physics or chemistry, PV equal to MRT, gas equation. So for the process 2 to 3, P2, V2, M, R, T2. P2 is given, V2 is given, mass is given, gas constant for air is known, you can always find T2. T3 is known. T2 is known, you can always find out T1. Okay. Heat transferred during process 2 to 3, isothermal expansion. This value is known to you. So later, I will teach you what is the work done or heat supplied during an isothermal process. That is, I should find out PV to the power of, PV equal to C and work done is equal to integral PdV, and dV is, P is nothing but C by V. So you can write C, dV by V we can write, and that I can write is equal to C ln V2 by V1, or in this case V3 by V2. So it is, C can be P1 V1, P2 V2 is equal to C is equal to P3 V3. Substitute that, you will get this value. So you know V2 is already known, we have to find V3. Here V3 we can find out, right? Also I know T2, I can always find out T1. Again, process 1 to 2. What is process 1 to 2? This is adiabatic compression. Process 1 to 2 adiabatic compression. Later we will study in the later chapters, thermodynamic processes. PV to the power of gamma is equal to C. So it is possible to find the relationship. Again, PV is equal to, MRT. Right. So it is possible for us to find a relationship between temperature and pressure for an adiabatic process. This I'll be solving later. This equation I'll be deriving. Just to solve this problem, I'm just explaining this. And gamma ratio of specific heat is nothing but Cp by Cv. But in your earlier classes in chemistry, you must have done these things. So I got the gamma value. Right? I know the P1 value. So MRT. So all these things means I can find out again V1. Okay. Heat transfer during process 4 to 1. It is 4 to 1 is isothermal compression. So in isothermal compression means, you see here 4 to 1 is this one. 4 to 1 is isothermal compression. Okay. Heat transfer during process 4 to 1 isothermal compression shall be equal to the heat transfer during process 2 to 3, that is isothermal expansion. Okay. Now isentropic process means, that is adiabatic process. No heat transfer takes place from the between system and its surroundings. You know that delta Q is equal to, or delta Q is equal to 0. So delta Q minus delta W is equal to du. So delta Q du is nothing but d u2 minus u1. So you know also that it is nothing but mcv t2 minus t1. This also I will explain. Mass is given, specific heat is given, temperatures are given. You can find out what it is. Right? Fine. You have got this. This value you have got. See here. Just substitute here. You will get this one. So during process 3 to 4, isentropic process. Isentropic means again adiabatic. I have not told you what is entropy and all. Don't worry about it. We will study this later. So definitely heat interactions are 0. So now the work done is nothing but change in internal energy. That is nothing but mcv into temperature difference. M is known, Cv is known, T4 is known, T3 is known. Just substitute and you will get this. So process 1 to 2, it is an isentropic compression. That's why heat transfer is 0 and you have calculate the work done. During process 2 to 3, heat transfer is given. So work is also given, determined. During process 3 to 4, what is process 3 to 4? This is expansion process, isentropic expansion process. That's why Q is equal to 0. Work done, it has been determined here. Process 4 to 1, isothermal process. So Q value is whatever value it was there, this was rejected. So minus 0.4 kilojoules, 40 kilojoules. So it's an isothermal process. Change in internal energy will be 0 because du means mcv t2 minus t1, t2 and t means t4 and t1 are equal. That will become 0. Heat is equal to work. So you will get this. So don't get perturbed. It can be later. The biggest problem over here is I have not explained work done, heat transfer during isothermal expansion, isentropic expansion, isothermal compression and isentropic compression, which we will be studying under the topic thermodynamic processes. There I'll be deriving all these kind of a thing and similar problem will work out there. Right? Here since we are working on Carnot cycle happens to have isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. We are just discussing this problem. Okay, these examples must have helped you how to find the efficiency of heat engine, COP of heat pump, COP of refrigerator by using efficiency of reversible heat engine, also using absolute thermodynamic temperature scale relationship, that is Q1 by Q2 is equal to T1 by T2. Using these two relationships, most of the examples can be solved. In the last example, it is not at all a difficult example. Only thing is, I have not explained so far how to find integral PdV work and how to find heat transfer for various thermodynamic processes. But whatever you have studied under your earlier physics or chemistry classes, using that as an idea, that is ideal gases, it is possible to understand even that example. So this completes the discussion on second law of thermodynamics. But the consequence of second law of thermodynamics, a concept called entropy, that we will discuss in the next session.